traveling. And let's discuss this last one. So this here, I actually don't like it as a question. It's a little bit vague in terms of this language here about leaving Earth. But I think the intention is the astronaut is traveling at 0.95 c to another galaxy 5 light years away as measured by the astronaut. What is 5 light years then? It's a distance. Is it what type of distance? We need to clarify. It's a proper distance. Is it? The astronauts traveling to the galaxy, are they at rest relative to the distance they're measuring? They're moving. They're moving from point A to point B. They are not stationary with respect to point A and point B. The opposite to time. Right, so this is where the question is a little bit vague. It says an astronaut leaves Earth and travels at speed. So they are making a measurement while traveling at speed. So if point A is here and point B is here, and they are traveling at a high velocity between those points, then the points will be moving relative to them. So the length that they measure will be relative length. Right, because the person on Earth is stationary with respect to the Earth, which is the thing they are using to refer to measure. They're measuring from the Earth to some galaxy. The assumption is that the galaxy is not moving relative to the Earth, that the galaxy is stationary. And again, this is why I don't love these questions. They're a little bit vague about some of those details. But if you were measuring the length of the spaceship, yes. So if an observer on Earth looked up and saw the spaceship, they would see the spaceship contracted. But the person on the ship would feel totally normal. Their ship would not look small, but everything around them would look contracted. Cool. Okay, so 0.95 c is their velocity. 5 light years is a relative length. They are measuring a relative length or a contracted length. And then the question is, when she arrives, she immediately sends a radio signal back to Earth to confirm her arrival. Determine how long after her departure observers on Earth would receive her radio signal. This is a really complicated question, and it actually gets bogged down in a lot of finicky details. I don't want you, if you see a question like this, to overthink it. I want you to just do the math and sort of just answer it, because it can get really weird when you start considering that the signal they're sending back is a light wave traveling at the speed of light, and then you start being like, wait, but what does that mean for the relative length and the time and stuff? You don't have to worry about some of that stuff. So as long as you can interpret this question correctly with relative length given there, and then you can calculate the time and you recognize that she experiences proper time because she's present at the events. She's present when she leaves Earth and arrives at the new galaxy. So she's present at both events and can measure those events with one clock. Okay, so she experiences proper time and then sends a radio signal back to Earth to confirm her arrival. Determine how long after her departure observers on Earth would receive her radio signal. It would be the time it took her to get there, as observed by Earth people, and then the time it takes for light to travel back to Earth at the speed of light. Not thinking finicky time dilation stuff. Yeah. So you don't then start thinking, but the radio signal is moving at the speed of light, so its time would be dilated infinitely. So it wouldn't experience time, so it would take forever. No, light just travels at the speed of light, and it doesn't get that weird. Okay. Again, I don't need a numerical answer to that. I just wanted to discuss that because it will lead us into what we're going to do next lesson, which is paradoxes, really well. Let's just quickly smash out these first few answers, though. Can someone give me the answer to question 1a? Does someone already have that answer handy? 0.06. Oops. 0.06c. Cool. Yep. 0.95c as meters per second. 285, or let's go 2.85 by 10 to the power of 8 meters per second. And that last one, you can see why I've been avoiding doing light year conversions, I imagine. You have to do 30 years into seconds, which you have to multiply by 365, and then multiply by 24, and then multiply by 60, and then multiply by 60. And you get, in the end, I'll do it quickly, hang on. So we're going to turn 30 years into seconds by multiplying by 365 to give us the number of days. Oops, 30, by 365. That's the number of days. There's 24 hours in a day. That's the number of hours. There's 3,600 seconds in an hour. That's the number of seconds. So we're going to multiply by that. Oh, I already have multiplied by that. So that's the answer. So it's that times by C Yeah. Yeah. So it's 2.84 by 10 to the power of 17. That's meters or kilometers? That's kilometers, is it? So 20 in meters, which would be 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I disagree. I think that's meters. Well, did you use C, which is meters per second? So then your solution will come out in meters, and you'll need to change your units to kilometers by dividing by 1,000. So you'll get by 10 to the 17 meters, and that will be by 10 to the 17, by 10 to the 14 kilometers. Are people okay with that? Yep. And then question 2, so we've got rest length, that will be proper length, L0, 40.0 meters. Note the 3 significant figures, but then the speed, V, is given as 630 meters. Oops. And that is 2 significant figures, so why they bothered making it 3 significant figures in the distance, I don't know. But anyway, calculate the length. So we want to know relativistic length. Relativistic length is just L0 multiplied by the Lorentz factor, which is 1 minus V squared over C squared. And when you do that calculation, you get an answer of 40 meters. Oh, because it's not relativistic speed. Right. You got an answer of 40 meters? So it's the same because you're only moving 630 meters per second, not 3 by 10 to the power of 8 meters per second. You're not moving at relativistic speeds. So, well, it should be, this is relative length, so it should be contracted. So you should get an answer of 39.9999999. 10 nines and then a 1. Yeah, so completely unobservable. You just said 40? Your calculator just spat out 40? Yep, so different calculators will do different number of sort of decimal places and rounding. All right. Let's talk about, what was the word I used? How do I import? What? Let's talk about this. Thank you, everyone. Looking up at the board. Nice and quiet for me. There's one more conclusion that we can draw from the postulates of special relativity, namely that speed always travels at the speed of light in a vacuum and nothing can travel faster than the speed of light. You might ask yourself why can nothing travel faster than the speed of light? If I chucked a very powerful jet thruster, or even a weak one, it doesn't actually matter, but if I chucked a thruster that ran off solar on some little drone and sent it out into space and ran that thruster for millions of years, it would constantly accelerate, right? We all agree with that statement? It's producing a net unbalanced force, so it will accelerate in the direction of the net unbalanced force, okay? And it will continuously accelerate, okay? You know F equals ma as an example, force equals mass times acceleration. You can solve for acceleration by doing force divided by mass. You will calculate some net force. It doesn't have infinite mass or something, so you just divide by the mass and you get some amount of acceleration. So for millions of years, this thing accelerates, but it will never reach the speed of light. How can that be possible? This is how. This is what that Lorentz factor does. And it turns out that our calculations for momentum might be wrong. Now, the initial interpretation of this was that there is relativistic mass. So just like time gets bigger and length gets smaller, possibly mass changes. And objects actually might increase in mass as they get relativistically fast. This is not the understanding we have now. We now understand that mass is constant, but our formula for momentum was wrong. Now, momentum is how much sort of energy we have in kinetic energy, as an example, multiplied by our mass, right? It's how fast we're moving times by our mass. You guys remember P equals mv, very simple formula. Momentum is equal to your mass times by your velocity. If you get faster, you get more momentum. If you are heavier, you have more momentum. It turns out that momentum is relativistic. It's not just P equals mv. You have objects with a rest mass, some mass that we observe at rest, and again, there is no relativistic mass. Some places on the internet are still perpetuating the idea that maybe mass increases, but this is not the case. However, the convention of referring to mass as rest mass has stuck around. So you'll see a little m0 quite a lot, rest mass or proper mass, but there isn't actually any sort of relative mass. That's not there's no evidence that mass changes. But momentum does. Momentum does change the faster you get. And when your momentum gets quite large, what that means in terms of the physics is the amount of force required to accelerate you any faster gets bigger. Okay, so when you have a lot of momentum and you're moving very fast, a tiny force will make a negligible difference to your velocity. It will accelerate you only marginally, right? And the faster you get, the more force you need to make a difference. Not the faster you get, the more momentum you have. Well, this Lorentz factor comes into play here. This axis I want you to think about as your velocity, okay? And as your velocity over c, which is the speed of light, and this is the Lorentz factor, remember, v squared over c squared, as that v approaches the speed of light or becomes c, if you look at your formula up here, as that becomes c, you get c squared over c squared, which becomes 1. With me so far? 1 minus 1 becomes 0. Square root of 0, I don't even know if you can do that. Is that undefined? So that's undefined. And then even if you could do it, you would get 0 on a denominator, which is undefined, right? So there is an asymptote here where we never actually reach that. And mathematically, that checks out. And experimentally, that checks out. We have not been able to accelerate anything with mass because it has a relativistic amount of momentum. And as the velocity increases and approaches the speed of light, the momentum approaches infinity. When momentum approaches infinity, no amount of force will accelerate the object anymore. It will just reach the speed of light at most. but never actually gets there. So that little Lorentz factor mathematically actually works with what we theoretically understand to be the case and what we have experimentally shown to be the case. We cannot, no matter how much we try to accelerate something with mass, reach the speed of light. Pretty cool? Bit weird? I don't know how you feel about that, but we're now going to talk about relativistic momentum. So if you could get a heading for me. Here we are. Now, fancy P is used, but it's fine to just use a capital P. It's much of a muchness, but I'm going to use the fancy P because I'm fancy. Not that fancy, but a little bit fancy. Now let me just double check that this matches your syllabus too. Yep, cool. So your textbook and your syllabus do match for the notation as well. So let's be clear about what all of that means. PV is relativistic momentum. Now, if we're giving you, because on your external exams, right, you'll have questions on linear motion and projectile motion and stuff like that. If we're giving you a question about Newtonian sort of situations, real world situations, you're obviously not going to be expected to use this formula. This is only if you're given a specific question about relativistic events, things happening at a fraction of the speed of light. M0, again, M0 is called the rest mass. And the reason it's called rest mass is because it's actually very hard to measure mass for moving objects. And again, some of the earlier ways of trying to do so seem to indicate that mass was increasing with momentum, but that is not the case. There is just a rest mass of objects, and then measuring that when things are moving is difficult. And v is just the velocity, so nothing really to talk about there. That should be fine for you guys. Let's do an example. That's pretty much all there is to this, and I feel like given we've done time dilation and length contraction by now, you're probably fairly familiar with how this is going to go. So I'm not going to spend too much time laboring the point. We will try and quickly finish this before the bell rings in 2 minutes. I know it's going to go pretty quick, but again, there is not much to this. So mass is mass 0, 1 gram, or what's that, 1 by 10 to the negative 3 kilograms, which is SI units. They give us the momentum, PV, 5 by 10 to the 5 kilogram meters per second. Units are literally kilogram meters per second for momentum. Find V. So we can quickly sub into formula m0v over square root 1 minus v squared over c squared. If you can, when that bell rings, just hang out for 2 seconds. We'll try and get this finished. So 5 by 10 to the 5 equals, let's immediately multiply that by the Lorentz factor. And we can solve for v in terms of c as well. 5 by 10 to the 5 equals... Okay, this is probably going to take a little while, so we might catch up with it next lesson. Hopefully you can see, though, that it is much of a muchness, same sort of thing. You can calculate velocities, you can calculate momentums, and nothing will ever go the speed of light. We'll finish it up next lesson.